Alright, let's do some calorimetry. Let's think about what we did here. We set up a little marshmallow, put him on a little thing, let him burn. Okay. In here we collected, we have H2O, we have a thermometer, right? And we have this guy burning, and the heat is going from here to here. Really, it's kind of like this, where you have the system and the surroundings. The heat is leaving from the system, going to the surroundings. So if the heat, the system is losing heat, it's a negative Q. It's giving off heat to its surroundings, which is positive Q. So usually the charge is opposite because it's in terms of the system. So this is the system, and this is the surroundings. The truth is that not all of this heat is absorbed into this. It's also absorbed into the air, probably into the metal. The metal can is absorbing some heat and also giving some off to the water, some to the air. So there's lots of places. If we could insulate this, we could keep most of the heat from here to here. The question is, how much heat is in here? Okay. Well, how much heat from the reaction? So in our case, the heat given off by the reaction is going to be negative the heat absorbed by the calorimeter. Okay? So we'll measure the heat from here and see what it tells us about the energy that's in here. Okay? Knowing that it's not going to be 100% efficiency. The equation for the heat of our calorimeter, that's what this guy is called, right? Because it measures heat in the form of calories, although we're using joules because we're awesome. The equation for all heat flow is going to be Q is equal to ms delta T. And in this case, remember, m is the mass of the substance, S is the specific heat of the substance, and delta T is the change in temperature. So say we have a calorimeter with 200 grams of H2O, okay? And say we heat up this marshmallow, which happens to weigh, we're going to burn 10 grams of mallow, okay? And say that our, so this is water, this is this, and our change in temperature is going to equal to, let's give it a nice big temperature change, 60 degrees Celsius. That's pretty good data, okay? So we're heating it up. Let's find the heat that the calorimeter absorbed. And we can measure that because we have the mass of the water, we have the specific heat of water, which is 4.18 joules per gram degree Celsius, and we have our change in temperature of water, okay? So the mass of the water is 200 grams times 4.18 joules per gram degree Celsius. That's just for water. And the change in temperature is 60 degrees Celsius. Knowing that it's final minus initial, so if the final is higher, we're going to end up with a positive number. If the final is lower, we're going to end up with a negative number. Okay, and that would mean like heat flowing into here. So you do your math. So the heat that this calorimeter is absorbing, what did I get? Something like 50,180. And the units, grams, are going to cancel. Celsius are going to cancel, and we're left over with joules. And we usually convert this to kilojoules. So 50.2 kilojoules, because we have 3 significant digits. What we do now, I gave that 60.0. All right. When in doubt, just use 3 significant digits, because most things in chemistry are that accurate. Okay. Now we want to say we wanted to compare it to the package, and the package says that for every that you get 100 nutritional calories, calories. I can't even spell today. Nutritional calories is equal in 130 grams serving. Just know that a nutritional calorie is actually a kilocalorie. So it's really saying there's 100 kilocalories in 30 grams for every 30 grams of marshmallow. Okay? So let's see if we can compare this guy to this. Well, first things, let's reduce that to get into how many kilocalories per 1 gram of marshmallow. Do the math. 100 divided by 30, it's going to be something like 3.33. Okay, I think that's right. Oh, that's right. That's good. Okay, so that's how many are in a marshmallow. Now we need to convert kilojoules to kilocalories so we can compare the two. The conversion factor is 1 joule, 4.18 joules is 1 calorie. And if I have 4.18 kilojoules, it's going to be the same as, so this is 1,000 of these, it's going to be the same as 1,000 of those, is 1 kilocalorie. Okay? So there you go, FYI. So let's convert this kilojoules to kilocalories and see what we got here. Okay? So what do we got here? So I've got my 50.2 kilojoules. 4.18 kilojoules is in 1 kilocalorie, and that is something like 12.0 kilocalories. And that's what I was able to absorb. So this is my experimental. Oops. And then this is what the package says. And this is really the heat absorbed, and this is what the heat that's in there, the enthalpy, the chemical energy that's usable as work and heat, but we're measuring mostly the heat because it's constant pressure, so it'll be the heat of this reaction, we'll call it. Okay? So this is what the package says, this is what we got. Let's figure this out a little bit more. Well, this is in kilocalories per gram, and this is kilocalories, straight up kilocalories, so let's just convert that to kilocalories per gram. 12.8 kilocalories, and we burned 10 grams of mellow. So our experimental is 12 divided by 10, what is that, 1.2 kilocalories per gram of mellow. Okay, so this is a better one to compare to this guy. So if we're going to compare the two, let's find the percent error. We can do it a few different ways. First thing is, let's see, we know that we had, how many kilojoules of energy? 50.2 kilojoules when we burned 10 grams. So let's figure out how much is actually in the package. So the package says that there are 3.3 kilocalories per gram. Actually, let's go to kilocalories because we want to talk that. Kcal, 12.0 kilocalories. So the package says that there are 3.33 kilocalories per gram. So 3.33 kilocalories per gram, and we have 10 grams, so that we should have 33.3 kilocalories, okay? But we only absorbed 12, so to find the percent yield, remember percent yield is experimental, what you get, versus the known value, times 100. So it's to see what percentage or how close are you to the known value. And in our case, it's 12.8 kilocalories over 33.3 kilocalories times 100. And that ends up to be something like 36%. You could also just use the same, you could compare the kilocalories per gram to find the percent yield. Experimentally, we found 1.2 kilocalories per gram divided by, well, what it really should have been is 3.33 kilocalories per gram. Everything's going to cancel. And you're going to get the same number. So it's a choose your adventure novel, okay, which is 36%. That's pretty good. Most stoves are around 30%. We, a couple of years ago, we did the efficiency of the camping stoves that the outdoor club has, and we got around 30%, which is not so bad.